Hello and welcome back to the Project Management PrepCast, where preparing for the PMP exam is easier and more convenient than ever. I'm your instructor, Cornelius Fichtner. This is an advanced lesson on quality management tools. We look at deliverables and work performance as inputs and outputs in the context of related processes. We distinguish often confusing terms for quality metrics based on the targets or ranges our customers wish to see as the result of our project. We apply tools to gather our project quality data, and then we explore selected tools to analyze the project quality data and report our findings. Certainly, you may have seen many of these tools and techniques used in the different quality management processes. This lesson is meant to bring your knowledge of these tools to an advanced level of mastery. What's our main concept? You must select appropriate models to analyze and report project quality. To help you distinguish between quality tools, this lesson presents how they are used. In the short term, this lesson will help you answer quality management questions quickly during your exam. In the long run, you should also be able to apply these tools effectively in your real live projects. I actually thought of calling this lesson More Fun with Charts. But seriously, the ability to analyze and report project quality can help you validate that the project meets the needs of the clients and assure your team is performing as efficiently as possible. Before getting into specific quality management tools, we want to give you the big picture and the context of where all the quality management related data and information is coming from. So we bring you figure 8-2 of the PMBOK guide that shows the interactions of the major project quality management processes. In terms of interactions by knowledge area, the figure also shows that there is an involvement of project integration management, project quality management with its 3 processes, project scope management, as well as other processes. At the highest level, we see that project quality management processes use as inputs the deliverables and work performance data, and as outputs we have quality reports and verified deliverables. But how did we get from A to B? How did these inputs become those outputs? We want to explore this a little bit. First, we need to understand the flow of deliverables. Figure 8-2 shows this at a high level. We have, as you can see here, deliverables as an input to control quality, and they then become verified deliverables as an output. But if we adjust the view a bit, we can more closely see what is going on. If we zoom further out and look at this from a higher perspective, we can see how the deliverables came about from project integration management. It starts with the requirements traceability matrix that comes from the collect requirements process. This is an input to the direct and manage project work process. One of the key outputs, as we saw, are the deliverables. These deliverables become an input to the control quality process, which is part of the monitoring and controlling process group that occurs throughout the project. To measure the deliverables against the project requirements, we are to use the requirements traceability matrix in this process with the goal of having verified deliverables as our output. These are then again a key input to the validate scope process, where we present the verified deliverables to the customer, and finally the deliverables gain formal acceptance by the customer and become accepted deliverables. So that's how the deliverables flow. Next, we want to talk about how work performance data flow through the processes. This is the data that we need to gather, visualize, and analyze with the aid of the various quality management tools. We see that the data goes through 2 transformations that interest us. First, work performance data are inputs to control quality, and the data is transformed into work performance information. Second, work performance information is used in the managed quality process to create quality reports as outputs. Does that sound familiar? Because we have seen this pattern before. Indeed we have. We have seen how data is transformed into reports when we discussed the project scope management knowledge area. In the scope management processes, we saw the flow from work performance data on the left to work performance information in the middle to work performance reports on the right. Through this process, raw data is transformed into meaningful reports that can eventually lead to the appropriate corrective and preventive actions. And when we lay out the situation from the project quality management knowledge area in a similar fashion, you should be able to see the pattern emerge even more clearly. Executing the direct and manage project work process gives us raw work performance data. As part of the control quality process, we then use data analysis techniques to produce quality control measurements and work performance information. These are used in the managed quality process to produce quality reports and recommend process improvements to maximize performance. So when it comes to the flow of information, remember that it occurs in three forms: raw data, actionable information, and clear reports. When you have properly used the tools and techniques of the managed quality and control quality processes, the result is an actionable form of information for project quality management. For example, what are the primary causes for rejections when the customer does not accept a deliverable? To what extent are requirements fulfilled? How much rework is required? What corrective action should we recommend in a change request? What verified deliverables do we have at this time? To what extent do the verified deliverables meet the quality standards we must measure against? And what process adjustments are advisable to remove impediments to progress and improve efficiency? In order to have actionable information, we need quality metrics to measure performance according to quantifiable goals. Now that you have the big picture and a better understanding of the context of where all the quality management related data and information is coming from, we want to dive deeper into some of the quality management metrics and quality management tools. Having quantifiable goals can sometimes be a challenge because there are three different terms in quality metrics that are often confused: tolerance, thresholds, and limits. Here is the bird's eye view of these things. First, tolerance. Tolerance is the specified range of acceptable results in a quality requirement. The specification is typically expressed with a target value and a tolerance value. For example, when the acceptable range is between 40 and 50, the tolerance specification is 45 plus or minus 5. Second, threshold. A threshold is a predetermined value of a measurable project variable that represents a limit, usually expressed as a percentage deviation from the target. Once our work performance measures reach that limit, we must take action. So we analyze work performance data compared to the variance thresholds in our project management plan component for risk and cost, such as an allowable cost overrun percentage. We analyze deliverable quality with similar thresholds in dimensions such as square meters. And third, we have limits. In a control chart, we have two sets of limit lines marking specific values or quantities. First, we have the outer, upper and lower specification limit values based on the customer's product acceptance requirements. And then we have the inner, upper and lower control limit values to trigger intervention during the project. Note that in our example here we show the outer red bands as the specification limit. Depending on customer requirements, the specification limit may be greater or less than the area defined by the control limits. You should be able to explain these differences to your stakeholders. To sum it up, we find tolerances around the target quality requirement with a plus or minus value. Variance thresholds are a percentage deviation that marks when to investigate or intervene, and limits are usually expressed in lines at specified values on a control chart. We have many ways to gather quality data, ranging from very low-tech to very high-tech. For this lesson, we look at 6 tools briefly. One of the most low-tech tools is the check sheet, where we tally up each incident of a type of defect. For example, you could tally up the frequency of each failure mode, the physical location of each defect, the sample measurement variation in groups of 5 millimeters, or the step in a procedure at which failure occurred. Forensic investigators use tracking labels and scanners to establish the proper chain of custody for samples taken from a crime scene. Websites and software applications use codes to track feature usage and interests. Tracking codes help us track inventory from manufacturers to warehouses to shipping carriers to our customers in a web order. We use sensors to automate data gathering. Our utility companies use gauges to remotely monitor usage of telecommunication data, water, natural gas and electricity so that they can bill us, but also intervene when pressure or traffic reaches a certain level. In demonstrations, we gather feedback from stakeholders to identify new requirements and validate deliverable quality. In retrospectives, the project team discusses the recent project or iteration to identify impediments to efficiency and quality development, along with suggestions for how we can do better. And sampling. Sampling involves inspecting a representative selection from the deliverables produced for the project so that we can measure and verify its quality. The tools you select depend on the needs of the project and the cost of quality. When it comes to sampling, it is important to be able to distinguish 2 kinds of sampling data. We have attribute sampling and variable sampling. So we begin with the attribute sampling. Here we determine if the sample item is defective or not. We may identify conditions that would indicate that the sample item is defective, such as the presence of a scratch, a warp, or a broken piece in a physical sample. Or perhaps if we're looking at a software module, perhaps there's the presence of a timeout or error code. Next, we have variable sampling. Here we measure how good, how bad, or how much on a continuous scale. We may measure time in seconds, weight in grams, contaminants in parts per million or percent, or color in wavelengths, and so on. Sometimes we may use variable measurement in attribute sampling. In other words, does the sample conform to the expected measurement or not? You may not even need to directly measure each time. For example, instead of measuring the diameter of a pin, you simply see if it fits into a test receptacle. If it doesn't fit, it's defective. Once we have quality data gathered, we have tools to analyze it and report our findings. The tools can be arranged by their various practical uses. With tools for classification, we group pieces of project data according to related attributes and find a name for the groups. With a few tools for sequencing, we sort project-related events in a logical order or draw a diagram to represent a process with its inputs, outputs, loops, and decisions to identify areas that are prone to defects, inefficiency, and non-value-added activity. With tools to analyze variances, we plot project quality metric data distributed over time, or we may group data in bars to mark frequency per item or per range of related attributes. With tools to analyze causes, our team can identify why quality issues may be occurring. With tools to analyze correlation, we can interpret whether 2 pieces of data have a positive or negative correlation and how significant it is or no correlation at all. And lastly, with tools to analyze relationships, we can segment, sort, and subtotal data by various attributes and use the information to prioritize elements of our plans or make other decisions regarding proposed changes. To arrange our quality data analysis tools into the categories named here, we actually use one of our classification tools, which is up next. We have seen classification diagrams as a data representation tool in the plan quality management process, manage quality process, as well as other processes, but we haven't seen them together. That's a shame, because you should be able to distinguish among these tools for your exam. Tree diagrams are not to be confused with decision tree analysis that is used in the Perform quantitative risk analysis process. With tree diagrams, we decompose hierarchies from a broad class to narrower categories and additional details, parts and tasks. We use tree hierarchies to organize project scope, schedule and cost with the work breakdown structure, and resources and risks with their own breakdown structures. A mind map is another technique we can use to visually organize hierarchical information. We label bubbles or images and radiate them from the center, adding more bubbles or labels radiating out as needed. It is often used to gather requirements and relationships as you create the quality management plan. In tandem with brainstorming, we use affinity diagramming to organize long lists of items where you don't initially know what the categories are. We use this technique to come up with practical use labels of tools to analyze quality data. Uncategorized items may be written onto cards or sticky notes. The team works to find affinities between these items, moving the items into groups that appear related. For the managed quality process, you can use these tools to organize the causes of defects, for example. In project quality management, we use process decision program charts, or PDPCs, to engage the team in anticipating risks that potentially affect the quality of our deliverables. PDPCs begin with a tree hierarchy based on some portion of the WBS. I realize this looks too small for you to read, or will at least in the end, but what's in these boxes isn't important. What's important here is the structure. The chart includes the lower two levels of the WBS, including select deliverable work packages. The third tier shows tasks identified in the define activities and sequence activities processes. For each task, the team is then brainstorming what could go wrong with the quality of the product deliverables and impede our efficiency in executing the work. The team documents the significant problems at the fourth tier. On the fifth tier, the team documents preventive and corrective countermeasures in thought clouds. In turn, we may need to define and sequence new activities to add to the schedule for the purpose of eliminating these risks. In essence, the process decision program chart further decomposes and elaborates on the existing work breakdown structure. And you thought that you only needed the WBS for scope management, didn't you? We're moving on to sequencing tools, where we have two diagramming tools where we sort project-related events in a logical sequence and analyze areas that are prone to defects, inefficiency, and non-value-added activity. First, we have activity network diagrams. This activity on node diagram is an example from the PMP guide. You may be thinking, why are we talking about the project schedule network diagram when this is a quality lesson? The answer is because you can use this diagram to identify the potential for quality issues in your process. Some tasks may overlap and be performed at the same time. If one person is assigned to multiple activities, it may result in resource overutilization, which may in turn contribute to burnout, errors in rushing that lead to rework, or overtime cost. And then, when the team examines the dependencies among activities, the total float in a path provides opportunities that allow lead time to overlap activities and compress the schedule. They should also identify any lags that add delay to successor tasks. The way we find these risks that may affect quality is by using the familiar precedence diagramming method, the critical path method, the critical chain method, or PERT, the program evaluation and review technique, along with schedule network analysis techniques. Our second sequencing tool that can help our project team anticipate potential bottlenecks, delays, and risks is the process flowchart. Here is an example of a flowchart starting at the top left and ending at the bottom right. Unlike common flowcharts, where it's unclear who is performing a specific task or making a decision, the role of the responsible party is clearly identified in the labels on each lane. So this is actually often called a cross-functional flowchart or swim lane diagram. Decision diamonds may indicate bottlenecks or rework where activities are often delayed by another party's decision or corrections. We may find potentially inefficient loops involving multiple decisions, rework, and redundant processes. This type of cross-functional flowchart is often used to try out new sequences or quality control checkpoints for process improvement. Next up are our tools to show how we present variable data from project quality metrics distributed over time or over groups. A run chart allows us for a quick visual analysis to see data over time. It can be used to see any ups and downs. For instance, we notice a problem every day around 9 o'clock. It turns out that around 9 a.m. several more machines are turned on our shop floor, causing a drain on electricity. A bar chart compares multiple factors. The bar lengths show how frequently each factor affected the result. In this example, we report the tensile strength of a product from selected suppliers before and after performing a proprietary technique. This allows us to compare 3 different suppliers for selecting in the next phase of the development. And then we have the histogram. This is a data representation tool that shows the frequency distribution for multiple ranges or sources. For instance, you can show employee performance issues occurring for various ranges of experience, such as 1 to 5 year experience, 5 to 10 year experience, 10 to 14 year experience, and so on. So, let's take a deeper dive into a special type of run chart. The statistical control chart shows us if a process is stable or that it has predictable performance. It is based on the run chart, but instead of marking variance in one metric over time, the control chart may show variances in a set of samples. The upper specification limit and lower specification limit mark what the customer specifies as the acceptable range of variation in deliverable quality measurements. The upper and lower control limits are always 3 standard deviations from the mean, which means that 99.73 of all our measurements should fall between these 2 lines. These give our project team an internal range. If any sample measurement goes above or below our control limits, we may need to consider an intervention. Among our samples, we expect some variation both above and below the mean due to common everyday causes. Experienced operators make occasional errors. Machines have fluctuations in ambient vibration, temperature, or electricity. Air has minute levels of dust and contamination that can affect the samples. On this particular chart here, among these samples, everything looks like it's running normally, but we have 4 more conditions that merit investigation. Which brings us to this new chart here, where we have another set of sample measurements, but with the same specification and control limits. And one of our dots here is clearly outside of the control limits. Granted, it's only one offender. Still, it constitutes what we call a special cause, and it is worth investigating to determine exactly what caused that particular sample to fail our control. It's not defective because it still meets the customer specifications, it's within the red lines, but falling outside the yellow control limits is a sign that we need to investigate potential causes. Next up is something that we call the rule of 7. Here we look for any sequence where the result of our measurements falls into the same side of your mean 7 times in a row. In this case here we have 7 dots in a row below the mean, and when this happens we need to investigate possible causes. These 7 instances out of all the thousands produced are statistically significant. They are a sign that the process is under some some skewing influence that may affect more than just the samples we take. Special cause and the rule of 7 are really the most common patterns worthy of investigation and study. But stay with me, I got a couple more. Here's our last set of sample measurements on a control chart with the same specifications and control limits, and whoops-a-daisy, one sample came in far above the upper specification limit. That, my friend, is a defective sample, and we need to investigate its cause. Our next pattern is that of a trend. We're looking for any run of 7 samples in a row where the values trend upward or downward. In this case, 7 dots in a row show an upward trend, even if the trend begins below the mean and ends above the mean. It's possible that these 7 trending points constitute a statistically significant trend, a sign of some skewing influence that led to the defect. And one tool that we use to analyze the potential root causes of our anomalies is the cause and effect diagram. There's a reason why this is also called a fishbone diagram. Some may argue that it works like a tree diagram, where we decompose categories in details. In this case, we start with a problem statement on the right and work backwards to identify potential causes along the relevant categories. The lines routing backwards look like the bones of a fish. This is also known as an Ishikawa diagram, named for the Japanese quality engineering guru Kaoru Ishikawa, who devised this tool for analysis in 1982. We have seen it in the control quality process, but we also use it for the identify risks process to try and determine root or main causes and contributing factors. If you don't yet have your categories to organize root causes, try brainstorming and affinity diagramming first. When a significant variance from our quality requirements has been detected, it is critical to find the root cause and ancillary causes. A cause and effect diagram will help you to do just that, so that we can then recommend preventive or corrective actions. Another tool we use to prioritize the top causes of quality issues is the Pareto chart, based on what we call the 80-20 rule. Back in the 18th century, an Italian economist named Vilfredo Pareto observed that about 80% of the wealth of the country was owned by only about 20% of the population. In 1941, an American quality guru named Joseph Juran called this pattern of distribution the Pareto principle, or the 80-20 rule. This rule states that for many events, roughly 80% of the effects come from 20% of the causes. This principle helps us to prioritize the top causes of quality issues for intervention. This example of a Pareto chart is sorted by the highest incident first, based on a check sheet that tallies 5 main causes for defective paint jobs. The line across the top tracks the aggregated percentage for all the causes, shown up to 100%. We can see that the chief reason, coating run, accounts for 80% of the defects tallied. Which of these problems would you address first? Would you focus on the big ones on the left or on the tiny ones on the right? Well, for the best return on investment, of course, you would focus on the big ones first. We are moving on to the scatter plot or scatter diagram. It is used to find a correlation between values, but unlike the control chart, we're not necessarily looking for performance over time. Here are some examples of scatter diagrams. Once we have 2 columns of values, we set up the scatter diagram to show a trend line. We're looking for values or dots that clustered together near the trend line, making up one of 3 patterns. The first pattern we're looking for is a positive correlation. If both variables increase or decrease and the trend line goes up, we may say there may be a positive correlation. In this case, there is a known correlation between age and weight until you hit puberty, but between ages 15 and 70, the correlation is weaker and weight distribution is more random. The second pattern is a negative correlation. In this scatter plot here, the dots are tightly clustered, and as the first variable of team tenure increases, the second value of released bugs decreases. We would hope that with more experience on our project team, the incidence of software bugs escaping our quality tests would be minimized. The third pattern we find is no correlation at all. In this scatter diagram here, all the values are quite randomly distributed with no clusters. In this case, we find the trend line almost completely horizontal. In other cases, we may find the trend line fully vertical for lack of any pattern to mark a trend. When we do not find any correlation, we need to measure a more significant factor. In the managed quality process, we may use scatter diagrams to determine what measurable relationships exist, if any, between any elements of a process, environment, or activity on one axis and a quality defect on the other axis. To display the strength of relationships among different factors, causes, and objectives, we can use matrix diagrams. Depending on the number of related groups, you can choose from different shapes. In the common L-shaped matrix, we use rows of one data group and columns of a related data group, like this stakeholder responsibility matrix. The common L-shaped matrix shows rows of one data group of matrix shapes and columns of another data group of relationship attributes. Another example we've seen is the schedule activity list with its attributes. The first group is related to the second group. In the Y-shaped matrix, we have three groups. The first is related to the second, which is related to the third, which in turn is related to the first group again, with fairly circular logic. You can see how the relationships go around almost in a triangle, but the headings form the shape of the letter Y. There are two more shapes that work very much like the L-shaped and Y-shaped matrix diagrams. For this pair of matrix diagrams, we have multiple data groups, some of which are not related to each other at all. The T-shaped matrix has an L shape embedded in it on its right wing, but also has another group of data on the left wing, much like the lower part of the Y-shaped matrix. However, the first group is not related to the third group. The X-shaped matrix has four L shapes embedded in it, with data relationships going all the way around. However, the first group does not directly relate to the third group, and the second group does not relate directly to the fourth group. If you can build a T-shaped matrix, you can easily build an X-shaped matrix by adding rows at the top and adding a new set of data labels on top. But for our last two shapes, all the data groups are interrelated. The C-shaped matrix is much like a T-shaped matrix with a three-dimensional element. It has three groups, all simultaneously related together in a cube. But this type of chart is difficult not only to draw, but also to interpret, so it is rarely used. In many cases, normal 3D column charts do the trick. In the roof-shaped matrix, we have one group of data related to itself. This matrix may use a simple legend of symbols representing a strong, moderate, or weak influence. Alternatively, it may show a positive, neutral, or negative level of support for each other. For example, functional requirements that are related to security all support each other, but requirements for ease of access may detract from the security features. This roof-shaped matrix is usually seen with column headings all related to each other. Therefore, it's normally used in conjunction with an L-shaped matrix or a T-shaped matrix. There you have it, the 6 matrix diagram shapes: L, Y, T, X, C, and roof-shaped. And now for this here. Here we have an example of a chart mixing several matrix diagram shapes. This is sometimes called the House of Quality chart because of the inclusion of the roof-shaped matrix. The chart is based on a method developed in Japan in the 1960s called quality function deployment. The original objective is to translate what the customers say they want in terms of quality into functional requirements, or what we want versus how we need to get it done. With such requirements and features, it is like a requirements traceability matrix on steroids. In this case, a series of T-shaped matrix diagrams has been added on 3 sides to show relationships between functional requirements and difficulty levels, weighted customer needs, and competitor analysis. This house of quality is a model that can be used to communicate requirements analysis with the team and stakeholders. To give you an idea of what information this house of quality maps out, how would you like a tour of this house? All right, here we go. The customer needs and prioritization ratings form the left side of a T-shaped matrix diagram. The technical requirements and features go across to form the right side of the T-shape. The middle traces the relationship between the customer quality requirements and the internal functional requirements, similar to a requirements traceability matrix. The roof-shaped matrix shows how strongly functional requirements are correlated. The symbols may represent the strengths of relationships or mutual support between features, which can help the product owner or manager present trade-offs in the next iteration of related features. On the right, another L-shaped matrix, reversed, captures how well the organization ranks against its competitors for each customer requirement. The bottom here forms another T-shaped matrix to provide difficulty levels for each of the functional requirements and relative weights. When using an agile or adaptive approach for project management, the product owner can use this type of chart in a customer or user workshop to prioritize requirements and functionality for upcoming iterations and communicate the result to the team. Let me share a most clever quote. Quality is free. It is not a gift, but it's free. The unquality things are what cost money. This is from Phil Crosby, the man behind the performance standard of 0 defects and the DERFT principle, which stands for doing it right the first time. Whew! We have reached the end of this lesson on advanced quality management tools. What did you learn? Among the often confused terms, we usually see tolerance with a target quality requirement and a plus or minus value, variance thresholds as a percentage deviation from the target, and limits as lines on a control chart. Process decision program charts build on the WBS to anticipate risks that potentially affect quality or performance. Likewise, swim lanes or cross-functional flowcharts help find bottlenecks and inefficiencies and plan countermeasures. On control charts, we measure variance and look for patterns in the sample measurements that skew performance and should trigger an investigation, including a special cause outside the control limits, the rule of 7 in a row on one side of the mean, or any run of 7 in a row trending either up or trending down. Using the cause and effect diagram, also called the fishbone or Ishikawa diagram, we start with a problem statement on the right and work backward to identify potential causes along relevant categories. The Pareto principle or 80-20 rule says that roughly 80% of the effects come from 20% of the causes. Once we tally up a check sheet of the main causes behind our anomalies, we use a Pareto diagram sorted by the highest incident first to prioritize our countermeasures. With scatter plots, a positive correlation trending up or a negative one trending down can help us find relevant factors behind our quality issues. No correlation is a signal to look elsewhere. And with matrix diagram, the most frequently used is the L shape, but we do have the Y, T, X, C and roof shapes that we can use either alone or in tandem. The bottom line is that when you analyze and report on project quality, you should be able to select appropriate models. Until next time.